Welcome to the micro communication course. Today we start a new topic, a read diode. So we have seen earlier that a gun diode and a tunnel diode. So both are working in a negative resistance region and in a forward bias operation. Now another diode we are going to start here that is or learn here that is about a read diode. So it will work in a reverse bias mode. Means your read diode is operated in a reverse bias. Now we see that how this reverse bias is constructed. So generally a reverse bias, it has a combination of n plus, then a p, then we have a I here, okay, then we have a flip. So we can say that this one is about a combination of a diode, generally it is used. And then that n plus, this we say that this one is about a heavily doped n plus region, heavily doped a p region, and this I is nothing but the intrinsic region. And this P, okay, it's not a P plus, only a P means what? It is about a thin region. So means your diode consists of N plus dash P dash I dash a P plus here. So that is about the sequence here we supposed to consider. Even we can manufacture this same kind of diode instead of N plus here. We can consider a P plus there and then N plus that. So we can design a read diode using the highly dopant material there. So now we see here how this diode works. So we supposed to draw a read diode and its structure now. So read diode structure that is about a n plus here. Then we say that we have the thin layer we supposed to say that is about a p now. Then we have the large layer that is about the I layer here, and then we have a p plus here that is about the I region or a intrinsic region here. Now here, if you consider that a first junction at a point of what where we supposed to consider that n plus p. This one is about a junction. That is about a first junction here. Or we can say that a first region. So in this first region, so we say that this one is about a junction here. So electron and hole pairs are generated in this region. Okay, so that's why this particular region it is about a thin. So that's why this particular region is supposed to be called as a avalanche region. Okay, so this one is the region here. We say that avalanche region. Okay, now this one is about a avalanche region. Now this one is about a avalanche region. Now here what happened here? So this junction is the formed by the using the what n plus p here. Okay, so means in this case what happened? So when we apply a sufficient DC bias voltage, so then in that case, so at this junction n plus and p region here, so we supposed to consider that a bias is applied here that is about a reverse bias. So that's why we supposed to consider that a reverse bias now. Okay. Now this one is about a positive one. This one is about a reverse bias here. Okay. So now this one is about a region here. So this n plus p region and another junction is about we say here that is about the I and p plus region. These are about the two junction. So but now this one region, so it when we apply the DC voltage here, when we apply the DC voltage here, so then what happened? So this one is about a positive here. So number of holes, okay, whatever the holes and electrons are generated here. Now this one n plus nothing but electrons and p is nothing but the holes we supposed to say. At this junction, what happens? That holes are transferring from this junction here. Means holes supposed to be moved toward this junction at this area. Okay, this one is about the area. Now here, the holes are moving at initially at this particular junction n plus p region here, and at that particular, because they get the sufficient energy from this ADC voltage. Okay, so electrons and holes, those both are getting the sufficient energy from this ADC voltage. So electrons here and holes will be propagating in this direction. So holes will be gathered at this particular junction. So large number of holes will be gathered at this particular junction because of that whatever the DC voltage we are applying there. Okay, so whichever we say it's supposed to be that there is a sufficient energy because sufficient DC voltage, and then above that particular DC voltage or at some sufficient DC voltage, this reed diode will work. Now here we can say that holes will be transferred at this particular junction, and there are some of the electrons are there, some of the holes are there. They will form the and a hole pair at this particular junction. So means we can say that holes and electrons. So at this junction, so the pair of the electrons and holes are generated there, and there will be a newly carriers are generated, and because we have the initial voltage we supposed to apply, and that because of that there are the carriers generated. When we apply again a further bias, okay, so what happened here? So these electrons and holes will get the energy from this field, and that's why that more number of electrons and hole pairs are generated. So that's why you can say that a multiplication process takes place here. Means we say that we here newly carriers are generated, okay, as well as that we have the earlier old electrons. Okay, so we can say that here, so this particular region, so number of electrons and hole pairs are created in this particular region. So that is called as avalanche. Now, why this called a? Because it is in which what happened. So holes and electrons pairs are generated, and that pairs are generated in this region, and that process is called as a avalanche multiplication process. Okay, in this region. So another region is about we say a intrinsic region and the AP plus region. So in this case, what happened? So whatever the holes are generated, that are moved toward the P plus region. Okay, here whichever the holes are generated there, so they are moving toward the AP plus region. Means this one is about the second region. So this one is about a first junction, another junction here. So whatever the holes are generated there, it is because of a higher supply voltage. Okay, then that holes are moving through this intrinsic region, and this intrinsic region is about what we can say I region here, or we supposed to say that holes are generated from this region and move toward the P plus region. So this I region is supposed to be called as a drift space region. Okay, or we can say that because holes are moving, okay, whichever the holes are generated here, that are moving through this I region, and this region is called as the drift region. So that's why we supposed to call as a that that electrons will drift through this region, and it will move toward this a P plus region there. Now we say that a bias is applied. So if the reverse bias is applied to this diode, it is more than the a breakdown voltage, then whatever the space charge region, that is we say that we say that we have the holes are drift toward this P plus region. So that is about this one is nothing but what a drift region or a space charge region. Okay. So if that breakdown, if that voltage apply here, that reverse voltage, reverse bias is applied here, that will be above the breakdown voltage. Then we say that a space charge region extend from this junction to the IP plus junction. So now this one is about a space charge. So that's why this particular whole region is called as a space charge region. So earlier we say that I region is about a drift space region. So instead of that we say that when that bias voltage is more than sufficient, then this junction and this junction here, so both the junctions and both the region is supposed to be called as a space charge region. And we supposed to say that holes are moving here. Now, next about what about the a field generated here? What is the field profile? What will be the dopant profile of this reed diode, and how this diode is going to be operate in the a reverse bias mode? Okay, so that we'll see. Now here we say that n plus p I p plus. This is about a reed diode structure. So another way we can suppose to obtain the reed diode using the another combination. That another combination is what? Instead of n plus, there will be p plus here. Then instead of p, there will be a n. Okay. Then a I. Okay. So then it will be a n plus. So we have the this junction. Okay. So p plus n. So likewise. So this one is about the another combination. Okay. So here we say that p plus n dash I plus n plus n. So this one is about the another combination of the error that read diagram. And here instead of a I region here, okay. So this one is about I region, that is about but here P region is here. Okay. In this case here is it is a P region, but here in this case N region is about a thin region here. Okay. This one is about a so carriers, whatever the carriers are generated, that will be drift through the I region toward the N plus region. So means at this particular junction P plus and N, whichever the carriers are generated, that carriers are drift toward this N plus region there. Next we talk about that a field profile here for the given particular region here. What is the field profile? So we say that this one is about the avalanche region. Okay, so avalanche region here, and then we talk supposed to be talk about that. Okay, what will be the a dopant here? Since we say that this one is about highly dopant here. Okay, so this region is about a highly dopant. We supposed to say right now. So now what about this a field profile? Okay, so what about your when we supposed to consider that a field profile here for this given junction? So in this case, we say that we have the a field means we supposed to say that at this particular junction it will be a maximum. This one is about a region here. So this one will be a maximum. That is about a field region, and then it will be gradually decreases there and throughout this I region. So this one is about a field profile of this given junction. So here in this case, if you see the figure here, so we can say that when we apply the reverse bias, so field will be a maximum at n plus p region. Okay, field will be maximum at n plus p region, and then it will be decreases. It will be decreases, and then throughout this region, okay, it will be remains constant. Throughout the region, that field will remain constant. And now this one is called as a because this is a constant one, so that's why it is called as a drift region. So this one is called as a drift region. So this one. Okay. Next is about a dopant one. What about the dopant profile? So since we say that, so we have the I, then we have the P here. So the dopant here, N plus region is highly dopant. Okay, this one is about N plus region, highly dopant. And then we supposed to say that this one is about a AP region. And then we have the very, very thin, very, very small region that is about a I region. So that is about a concentration. So we supposed to say that 10 to the power 13. Here we supposed to say that 5 into 10 to the power 16. And here we supposed to dopant concentrate that is about a 10 to the power a 20. Okay, that is about a dopant concentration. And then same dopant concentration here in the AP region. Okay, this is about a dopant concentration in the a P region. So we need to adjust a dopant concentration in a given diode so that avalanche multiplication will be occur, and that avalanche multiplication will be confined in a narrow region. Okay, this one is about a thin layer. We supposed to consider that is about a narrow layer because this one is a thin. So here avalanche multiplication will be confined in n plus a p region there, and then because of this, so we supposed to say that electrons generated in this particular avalanche region here, whatever the electrons are generated in this avalanche region, so that will be moved toward the n plus region, and the whole whatever the holes are generated, that will be drift toward this holes drift toward this AP plus region. Okay, so we supposed to use a proper dopant material here in plus and P plus. Okay, at this particular, so that the avalanche multiplication will be it takes place there, and then the holes are drift through this particular space charge region toward the P plus region here. So we supposed to say that holes are drift from this region, so it has some velocity, and that velocity is supposed to be called as a drift velocity, and drift velocity is a equal to a 10 to the power 7 centimeter per second. That is about the drift velocity, and a transit time can may be expressed here. Okay, so here we can say that transit time will be expressed in terms of what will be the a length. Okay, that is about a drift region we supposed to consider, and then what will be the a drift velocity. So this way we will get the a transit time there, and the breakdown voltage required at this n plus p junction so that a avalanche multiplication will be takes place. That breakdown voltage is equal to, that depends upon that what will be the resistivity of this material, then a mu n is nothing but that electron mobility in this region here, and the a permittivity here. So epsilon s is nothing but the a semiconductor material and its permittivity, and E max, that is about E max is the maximum breakdown electric field. Okay, maximum breakdown electric field, that is about a field we supposed to consider seen earlier in a graph there, and we supposed to consider that a E max because we supposed to say that a field in that region for the breakdown. So that's why E max of a B is the maximum breakdown electric field for the given region. And that will be, we supposed to say that for a given particular region by 2 here. And this one, that will be whole is nothing but a square here. Okay, A max square. And the multiplication, we supposed to write that what will be the multiplication factor or a avalanche multiplication factor, that is depending upon that what will be the voltage we are applying, and what will be the breakdown voltage with respect to that, what will be the value of n is depending upon that which material we supposed to be used here for the manufacturing of the this reed diode. So that is about what we can say that a multiplication factor m, and this n is equal to 3 to 6 for the silicon. Okay, if supposed to be used, if we use that a SI here, so in that case, the n will be depending upon the 3 to 6 there. Again, that n is again depending upon that what will be the dopant concentration we are using at this n plus p junction there. Okay, so that is about a reed diode. Now, how this reed diode is to be used? Okay, how it is to be used? So, for that purpose, we supposed to consider that a structure of the reed diode. So, how this voltage and currents are generated in this particular reed diode. So generally we supposed to use this reed diode along with the micro resonance structure, and this is supposed to be considered that it is to be operated in a negative resistance region. So that's why we supposed to use here a DC field, that is whatever the DC field we supposed to apply, as well as the AC field there. Okay, so now this one is about the AC field here. So that is we supposed to call as a VA. And then voltage and current here for the given particular diode we can draw here right now. This one is about, suppose we say that, okay, draw it now, and what will be the a transit type. So everything we'll see now. And what will be the value of a voltage and a current in the area diode now. So now generally we supposed to consider that a voltage we supposed to apply here, that is at this point here supposed to be a maximum here. We say that this one is about a maximum, and this one is about a P region here. So in that case, so it will be 0. Okay, this will be the positive half cycle. And then here we supposed to consider that it will again a positive now. So in that case, in this E region, I region, intrinsic region. So in this case, it will be supposed to be a negative now. Okay, this one is about it. So here we supposed to consider that a P region now. Okay, so likewise. So that is about your a voltage pulse. Okay, so this one is about your Vmax. Okay, so whatever the AC voltage supposed to be applied. And then we have the, we supposed to consider that a current now, because when we apply some particular bias voltage as well as the AC voltage to the along with that, what we can say that a reed diode generally it is to be mounted in a micro resonance circuit, and that micro resonance circuit is operated at the whatever the reverse bias voltage, and this AC voltage. So we supposed to maintain the both the things here. So that is about the breakdown voltage as well as the AC voltage. So once we maintain this, so that we will get the a sufficient output. Okay. So for that purpose, we supposed to consider that what will be the a DC voltage we are applying. So generally we say that a DC voltage applying, that is nothing but a at the breakdown voltage, and AC voltage supposed to be applied, that will be at this breakdown voltage. So means a DC voltage, DC field as well as the AC field, both applying at this particular diode, that will be equal here. Okay, so means DC as well as AC is supposed to be equal there, and the DC voltage applying, that will be a above the reverse breakdown voltage. Okay, that means whatever the voltage we are applying, that DC voltage, that will be above the reverse breakdown. Then this one is about a, what we can say that here in this region, that N plus P region, electrons and hole pair are generated. This was in this particular region, means at this particular junction, holes and electrons are generated, and this is supposed to be a multiplication region. Okay, means it carriers are multiplied in this particular region. So in this case here, so we supposed to get the more number of carriers are, so that's why we supposed to get the higher value of a current. Okay, we supposed to get that a higher value of a current. Okay, so now what will be the current? Now we talk about that a current value. So initially we say that at when we supposed to apply the breakdown voltage here, so current start increases. Okay, so current start increases exponentially, and it will be a maximum. So at this particular junction, okay, current start increases, exponentially here, and it will be maximum at this junction. Okay, so it will be a maximum. And then what happen here? Then current start decreases. Why current start decreases? Because the carrier concentration, we say it is increased in this junction only. So that's why the current will be maximum. So carrier current. Okay, so carrier current here. So it will be a maximum because carrier generation in a avalanche region will be maximum. And in this I region, no carriers are generated. So that's why the current in this region, carrier current will be a zero. So here carriers are generated, more number of carriers are generated in this avalanche region. So that's why the current is maximum. Then because n plus p region, so that is about a avalanche multiplication region. So that's why I0 will be increases exponentially and then gradually decreases. Exponentially, it will be decreases. Then in another case, what will be the current in this I region? Okay, so we supposed to consider that for a positive half cycle of AC voltage. Now this one, everything is occur. We supposed to say that a positive half cycle and that a current is increases. Okay, then what about the negative half cycle? So then negative half cycle here. So in this case here, so as compared to the whatever the DC voltage we are applying, so negative voltage is supposed to be opposing to this DC voltage here, and that's why the total voltage across this particular diode will be drops below the a breakdown. Okay, so total voltage across this particular diode, so that will be drop below the DC voltage. So that's why the avalanche multiplication stops and the carrier current drops. Okay, that's why avalanche multiplication stops and a carrying current will be dropping. So here up to the positive half cycle here, so we're supposed to consider that there will be exponential increasing in the current. Okay, then current decreases. Okay, so we're supposed to say that at the negative half cycle that current is going to be decreases because a avalanche multiplication stops because of that overall voltage or voltage across this particular diode will you drop as compared to the whatever the breakdown voltage. And then that carrier current here at this junction here, if you see that it will be looks like a pulse at this n plus p junction. So that carrier current will be it looks like the pulse there here, and that pulse is of a very short duration. Okay, pulse is of a very because this one is about the avalanche region. So that's why the pulse will be of a very short duration. And we say that a maximum number of carriers occurs here. Okay, maximum number of carrier generated. So that's why the current will be maximum at this particular region. And and then again we say that this one is about we can say that we have the end of this one is about a negative upside. But here because that holes are we say that more number of carriers are generated that carriers are drift toward this AP region. Okay, so that's why because of that there will be because of holes move toward this P region. So because of this they induce some current and that current is called as a induced current. And that induced current is it is depending upon that drift velocity of the holes that is Vd and what will be the length of this that drift region length. So that's why we say that it has a carrier current as well as a induced current. So induced current here we supposed to consider because it will be generated because holes are moving from this region. So that's why there will be a induced current. Okay, so I just supposed to draw here. Okay, so don't worry about what we supposed to consider here. So this one is about because holes reach in this region. So that's why it is about a current. So that is about a what you can say that IE of t. So that is about the induced current. So IE of t is equal to what will be the Q here, okay, for this region, or we supposed to consider that what will be the drift and what will be the length. Q is nothing but what? For a given particular cavity. So it has some resonance there. Okay, it has some resonance. Means holes move toward the negative, because this one is about this one is negative and will be for this given junction, because we are applying the reverse bias. So this will be a positive one and this will be a negative. That's why the holes will be attracted at this particular negative. And this one is about the induced current. Current is propagating through the diode. And this induced current, it will be a constant here, because this current is propagating because in this particular region here. So that's why, so if we consider that a diode with any external circuit there, so we are supposed to consider that induced current is propagating through the external circuit there. Okay, and that is nothing but a current propagating through this a space charge region. And this one, if supposed to be, we talk about that a current here, carrier current. Okay, this one we supposed to consider that a carrier current, and this one is about induced current, and both the current, they are according to the whatever the, we say that according to the AC voltage here. So that induced current will be a delayed by the a 90-degree. This one is about positive half cycle. This one is about a negative. So that's why we supposed to consider that as compared to the whatever the, we supposed to use this notation according to the whatever the AC voltage and a DC voltage. In in terms of that, we supposed to say that we say that a induced current will be delayed by the 90. Now, how it is to be delayed by? Generally, we say that this one is about the start of the pulse here for the AC. So at this, it will be a pi by 2. It will be a maximum. So at this, it will be a pi. Okay, means pi by 2 to pi. So that's why we say that it will be delayed by the a 90-degree. Okay, so carrier current as well as that, but you can say that a induced current here. Okay, so that will be delayed by the 90-degree. And so we say that overall current. Okay, if we talk about that whatever the current is generated here by this one is about a pi here. Okay, and then this one is about supposed to be 3 pi by 2. This one is about a 2 pi here. Okay, so likewise, so means here a carrier current generated, it is about a, at this case here it is about a 90-degree now, and induced current is about delayed by again a 90-degree. Okay, as compared to the whatever the carrier current there. So that's why if you compare with the AC voltage, so then it will be a, from this to this, it is about a pi now. So that's why relative to the AC voltage, so induced current from this we supposed to say it will be of a variation with a phase is about a 120-degree. So a current propagating through the external circuit, that will be out of phase with the AC voltage, and the negative resistance occurs in this particular diode. So that's why we supposed to say that to achieve the negative resistance, the time period of the AC voltage, that will be equal to the twice of tau, or the equal to the oscillation frequency. Okay, so that is what our tau. Tau is nothing but what? What will be the a transit time? Okay, so that is about a tau here. So we consider that tau earlier. That is about, it is depending upon that length and a, what we can say that a voltage. Okay, that is about a drift velocity. Okay, drift velocity, because of the, that is about the electron. So L is about the length and Vd is the drift velocity. So that's why, so this is about what you can say a transit time. So to achieve this, whatever the diode is to be work in a negative resistance region, so in that case, the time period of this AC voltage, that is to be equal to the twice of tau here. Okay, so that oscillation will be occurring. And we supposed to consider that here external current Okay, in the form of this one is about a carrier current, and this one is about induced current. So if you compare that, the external current that propagating, that will be of in the shape of a square wave. Okay, that's about a square wave shape here. Now then, what will be the efficiency here? Okay, what will be the a power efficiency, and what will be the a power of this particular reed diode? So generally we say that in a reed diode here, so there this one is about the avalanche region. Okay, so that's why we can say that a avalanche multiplication takes place in this region. So means a reed diode operating mechanism is nothing but the impact ionization. Okay, impact ionization, as well as we supposed to drift that holes through this region. That's why a transit time. So impact ionization and a transit time. So reed diode is nothing but a family of a impact diode. IMPA. So impact means what? A impact and ionization and a transit time there. Okay, so that's why it is called as a impact diode here. Then we talk about that what will be the power and maximum output power that can be expressed is supposed to be a PM here with respect to what will be the VM and a IM. So that is about the for a given particular frequency there, the maximum output power of a reed diode, that is depending upon that what type of a material we are supposed to use and what are the impedance levels in the microcircuit. So impedance levels in the microcircuit, it is depending upon that cavities and all. Okay. So we supposed to write here the maximum power, that's about a PM, in terms of a maximum voltage applied across the diode as well as the maximum current is propagating through the diode. So that's why we say that PM is equal to VM into IM. So how we can find out the VM? VM is nothing but what? What will be the maximum voltage we supposed to be applied to this a length, given length here. And a current here, that is nothing but a drift space region, drift velocity. Then we supposed to be consider here what will be the a permittivity here. So what will be the maximum bias, and that is about a given particular a region. Okay, that's why we say that avalanche region. That is about a length L here. So this one we supposed to consider that for a given particular read diode, that is about your a power. Okay, and then we supposed to write a PMVM here. So we'll get that a PM here. Okay, I'll just write directly for this region here. Okay, so A, that is for the avalanche region. So that's why generally A is nothing but here a junction form across this particular diode here. So that is nothing but a there will be some capacitance across the junction. So that's why it has a capacitance. So capacitance is nothing but what? Epsilon A into L here. That is about the length and the area here. So we calculate here a PM. Okay, we supposed to calculate that a PM is equal to what? A EM square PD into epsilon S into A. Or we supposed to write here, in this case, that will be a, what will be the, in terms of a capacitance also. Epsilon A is nothing but a CL. Okay, so this one, we will get the value of this a PM here. And then a efficiency. Okay, so efficiency I'll write here. So efficiency is equal to, what will be the PAC and a PDC here. So we'll get the efficiency for the given particular time. And that PAC is nothing but whatever the we have the voltage and current, and what will be the VDD ID. Generally, it is nothing but what? For the read diode, so VA by VD is equal to that ratio VA by VD is approximately is equal to a point 0.5. Okay, and the ratio that IA by ID is equal to approximately or equal to a 2 by pi. So that's why the efficiency, if you calculate here, so we'll get that efficiency is approximately, that is about a zero point 0.3. Okay, that is about the efficiency of the a reed diode. So means we say that a reed diode is about a 30% of its efficiency here, and here that reed diode is to be worked in a given particular breakdown voltage, or we can say that a reverse voltage there, and we say that that ionization, impact ionization takes place in this phase charge region there. Okay, so that again one more factor is about the frequency there. So efficiency of that diode, reed diode, that is depending upon the a frequency also. Okay, so we supposed to say that at a high frequency, what happened to this particular region, particular material. So there is supposed to be considered that a skin effect as well as what will be the reverse current is propagating through the diode. Okay, so that's all about a reed diode here. So we have learned a reed diode, and reed diode is nothing but the one family of the impact diode. So we supposed to be consider that a impact diode and its family here, IMPA, TT, transit time, impact ionization. Okay, impact ionization, transit time diode. Okay, so that's why impact here. And we say that impact diode is nothing but what is a one family of a reed diode, or we supposed to say that a classification of impact diode. We say that a P plus, I, N plus, then a reed diode. Okay, then another is about, we can say that linearly graded junction diode. Linearly graded junction diode. Then another is about a abrupt junction diode. Then this one is about a PIN. So we have seen today that is about a reed diode. Okay, so there are the two types we supposed to consider, that I, N plus here, and we have seen right now that is N plus P, I, and a, sorry, a N plus. That is about a, we supposed to see today. This one we have seen now. And this linearly graded junction diode is nothing but what we can say that N plus dash N dash P dash P plus, or abrupt junction diode. Okay, abrupt junction diode is nothing but what N plus P, P plus, and P plus dash N dash N plus. Okay, so now that's all about what we have learned today. That is about the a reed diode here. So we talk about that family of impact diode and how that impact diode is going to be constructed. So impact diode, we supposed to talk about that a P plus, okay, region or N plus region, that is to be considered here. So we see that that is about the another junction, or that is about the abrupt junction, a impact diode that we'll see. Okay, so the PIN diode, that is about, these are about the construction. So we talk about this N plus P, N plus P, P plus, or P N N plus. That is about a impact diode. We will see in a next lecture. So that's all about a impact diode. So generally that impact diode are used to provide you the highest output as well as the highest efficiency there. And all the diodes in this impact family, both are work in the reverse breakdown region there. Okay, all the diodes are work in the reverse resistance region, and these are the a supposed to be impact diode work in a micro oscillator there as a source. Okay, means we say that instead of using a gun diode, we supposed to be consider that a impact diode that is used as a oscillator there, or impact diode is used in a radar there. Okay, so likewise we learn That similarly we have seen a read diode earlier. So read diode is work as the oscillator there, or that is to be used in a radar there. So with this, stop here. So thank you all of you.